Good day, everyone. Welcome to session S24. And this is a section sponsored by the Chinese Institute of Probability and Statistics in Taiwan. And I am Yen-Shiu, the organizer, and also the president of the organization. And it's very honored and excited to participate this event to celebrate and honor the contributions from women in statistics and data science. And in this session, we have 3 speakers, and their talk information are given here. And also you can find more information in the program book. And we have Miss Yuting Fan, and she is a PhD candidate from Ming Chiao Tung University. And we have Yen-Shiu. She is a postdoc at Academia Sinica. And the last speaker is Meihui Guo. She is a professor at the Department of Mathematics from Sun Yat-sen University in Taiwan. And I think our section title is Methodologies in Time Series and Spatial Statistics with Applications. And let's get started. And I think Yuting, you can give your talk now.
Hello, everyone. I'm Yuting Fan from National Ming Chiao Tung University in Taiwan. First, I would like to thank the Caucus of Women in Statistics and Data Science for hosting this conference. And also thanks Professor Shi for organizing this session and inviting me to share my research with my advisor, Professor Huang. I'll be introducing how we use a generative model called diffusion models to forecast electricity load in power systems. First, I will define the goal of this research. After that, I will introduce the methodologies in detail. Then I will present the results of our data analysis. Our goal of this research is to predict future electricity load and derive prediction intervals to quantify uncertainty based on a single time series. Traditionally, AR models, Riemann models are used, but we are exploring state-of-the-art diffusion models, which have shown remarkable performance in computer vision and large language models like Midjourney and ChatGPT. However, one common challenge with deep learning is the need for large data sets. In our case, we only have a single time series. So to overcome this, we use a rolling window approach to create multiple observations, making our data suitable for deep learning. Let's start with the concept of generative models. Have you ever used any AI image generators? This is how they work. We provide a prompt, and the image generator will create a synthetic image based on its understanding of the prompt. You might wonder, is this image fixed? No, when you input the same prompt, the image generator will create a different picture each time. This happens because the model behind the generator is trained to match the data distribution. Each time we provide a prompt, the model also picks random numbers and from a standard normal distribution and transforms them into an image based on the prompt. If the image is 10 times 10 pixels, the model produces a 100-dimensional conditional joint distribution given the prompt. Depending on how the transformation is done, there are many types of generative models, such as GANs, VAEs, and diffusion models. So, how exactly do diffusion models perform this transformation? The idea was first introduced by Sol Dixon in 2015. Diffusion models have two parts, the forward process and the reverse process. In the forward process, noise is gradually added to the data in steps until it looks like random noise. This process deconstructs the data in a controlled way. On the other hand, in the reverse process, the model learns how to remove the noise step by step, basically doing the upside of the forward process. By learning to remove the noise, the model can generate new synthetic data from random noise. But how does the denoising module actually work at each step to remove noise? In 2020, Ho proposed denoising diffusion probabilistic models, or just DDPM for short, and they simplified the denoising module. First, a neural network is used as the noise predictor to predict the noise from the noisy image input. Then, the noise prediction is subtracted from the noisy image. This results in the output of one step of the reverse process. Depending on data formats and problems, we can select the appropriate neural network. So this is why diffusion models are so flexible. Until now, we have only talked about generating image without any prompt. However, in practice, it is important to control what to generate. Just like the previous example, we want the synthetic image to match the prompt an apple on the table. One simple way to do this is to add the prompt as a condition to the noise predictor, and everything else just remains the same. In 2023, Alcaraz and Stradov proposed a conditional diffusion model for time series imputation and forecasting called SSSD models. They inserted state space models into the noise predictor, which is a neural network as mentioned earlier. This allows SSSD model to capture the structure of time series data. Suppose we use an hourly data set and want to predict the next 24 hours based on the previous 7 days, which is 168 hours. The goal of SSSD model is to learn the 24-dimensional conditional joint distribution given the 168-dimensional data. Diffusion models can approximate distributions, but when we analyze the load data, we notice an issue with the prediction interval. It seems not correct. The coverage rate is an index to evaluate the validity of prediction intervals. It is the proportion of intervals that include the true data. The issue is that the coverage rate was too low due to narrow interval. So to address this, we decided to calibrate these prediction intervals. Conformal prediction is the method we need. It was first proposed by Gaverman, Vogt, and Van Peek in 1998. It provides confidence intervals for any point predictor, which are guaranteed to contain the true data with a specified probability. Sorry. This is a fully data-driven method. The only limitations are that the data must follow exchangeability and the predictor should treat all data equally. Recently, there have been several versions. I will introduce the widely used split conformal prediction method and to show how to use it build valid 95% prediction intervals. Suppose a training data set and a test data set contain independent variables and dependent variables, which are shown in x-axis and y-axis. First, we randomly split the training data into a training set and a calibration set. Then we use the trend predicted. Then we train a point predicted on the training set. Then we use the trend predicted on the calibration set to get the predictions. Next, we need to define a score function and calculate the scores from the calibration set. The score function is designed based on the problem to show the difference between the predictions and the true data. A higher score means the prediction is this accurate. So in this case, we just use the absolute residual. Among these residuals, we find out the 95% sample quantile, which is Q alpha here as the margin of error of the prediction interval. Then the predictions plus and minus the 95% sample quantile give the upper and lower bounds of the intervals. We applied it to the test data. The coverage rate here of the test data is 96%, which shows the validity of this method. So this is the concept of split conformal prediction. Returning to our case, we have already had prediction intervals from the SSSD model, but they are not accurate enough. So we calibrate the existing intervals using split conformal prediction concept for both bounds, which we called the conformalized prediction interval. The key point is that in split conformal prediction, we create the margin of the error for the interval, while in the conformalized prediction interval, we adjust intervals directly. Here is an example similar to the previous one. We have a training data set and a test data set with independent and dependent variables. We randomly split the training data into a training set and a calibration set. The 95% after training on this training set, we get the trend generative model, and we applied it to the calibration set. So we can get the 95% prediction intervals from this calibration set, and we show them as red bands. As we can see, they are too narrow, resulting in a coverage of only 60%. So to address this, we designed two scores functions. The first is the lower bound minus the true data, and the second is the true data minus the upper bound. We calculate the scores and then find the 97.5% sample quantile for each, which gives us QL and QU respectively. Next, we adjust the bound. The lower bound is subtracted by QL, and the upper bound is added to QU, which forms the calibrated interval. We also applied the trend generative model to the test set and get the prediction intervals. Then we subtract QL from the lower bound and add QU to the upper bound. This gives us the calibrated 95% prediction interval. As we can see, the coverage rate is 94.67%, which means the approach effectively calibrates the existing intervals. Now we have covered the methodology. Let's move on to data analysis. We use the hourly electricity load data from the New York Independent System Operator spanning 11 years and covering 11 zones. And to align with things work, we use the last 73 days as test data. Because we want to predict the next 24 hours based on the previous 7 days. We reconstruct the time series into several observations with a length of 8 days rolling window. We remove the non-positive values and normalize each observation by subtracting the mean of the previous 7 days and dividing by the standard deviation. Here is the prepared data. We have more than 4,000 training data and 73 test data. We conducted 4 experiments in this research. First, we trained models separately for each zone. And second, we treat load data from 11 zones as a multivariate series and trained only 1 model. Third, we combined all observations and without considering the zones belong to and trained 1 model. Fourth, we use the mixed model as a pre-trained model and fine-tuned it with the data from each zone separately. And we compare the mean absolute percentage error to Ding's research. On the left side are our 4 experiments, and on the right-hand side are the results from Ding's research. Our analysis used only the electricity time series data, while Ding's research included many variables such as the day of the week and temperature and more. In most zones, we perform better than SVM, which is the support vector machine, ANN, which is artificial neural network, and SVM. In zone NYC, all of our results outperform their results. We think this is a very exciting result because we achieved these predictions without using any additional variables. Okay. Here are 4 prediction results from our test data. The blue bands are the 95% prediction intervals of 100 predictions from the trained SSSD model. We are not satisfied with this result, so we calibrate the intervals using conformalized prediction intervals. The red bands are the calibration results. As you can see, the intervals are widened and to cover the true values. Here is a bar chart comparing the coverage rates of 95% prediction intervals for 24 hours. The blue bars show the results from the SSSD model, and the orange bars show the results from the calibration, which range from 0.92 to 0.99. This shows the calibrated intervals are quite valid. Additionally, if we use the median of the calibrated prediction interval as the new point prediction, the MAPE is even slightly lower than the results from the SSD model. So to summarize today's talk, we explore the use of diffusion models to predict electricity data and use conformal prediction to quantify uncertainty. Thank you for your attention.
Now I didn't see any questions from the board. So if there is no questions, then we can move to the next talk.
Thank you.
Thank you. Okay, so now Yen-Shiu, it's yours.
Okay. Good day, everyone. I'm Yen-Shiu Chin from Academia Sinica in Taiwan. Today, I will be talking about covariate-dependent spatial-temporal covariance models with applications through environmental data. I would like to acknowledge my advisors, Professor Xu from National Tsinghua University and Professor Huang from Academia Sinica. This research has been published in Spatial Statistics, and you can access the full issue on their website. Material variables may affect the distributions of environmental or geophysical processes. Anaja points out that pressure, wind speed, wind direction, temperature, relative humidity, and solar radiation can affect ozone formation and the distribution. We can also observe the clear variation in the covariance structure with meteorological variables. For example, we graphed two empirical covariance matrices for local scale PM 2.5 data in Taiwan, according to two different intensity of wind speed. We can see that the covariance value have smaller magnitude under stronger wind conditions. It's providing evidence that the spatial covariance structure is affected by the intensity of wind speed. However, there are few studies on stationary spatial covariance models that can vary with covariates. One challenge is that a spatial covariance function must satisfy the positive definite condition. The existing papers have limitations. Some models are restricted to specific meteorological variables, and some models are under the Bayesian framework and rely on MCNC methods, which are computationally intensive. So our goal is to develop a spatial temporal covariance model that allows the covariance structure to flexibly change with covariates and has a relatively quick and stable algorithm for parameter estimation. Let Y be a spatial temporal processes of interest with S indicating a location in the spatial domain D, and T representing time. Crazy in 2010 proposed the spatial temporal random effects model, the STRE model, which consists of two components. The first part is the mean function, and the second part consists of a vector of spatial basis functions B and a vector of random effects eta t. And a vector of random effects eta t follows a vector autoregressive model of order 1. Here, HT is an autoregressive matrix. CT is the innovation vector, which follow a Gaussian distribution with mean 0 and the covariance matrix VT. And is independent of the CT T point T minus 1. We propose a covariate-dependent covariance model built on this STRE model framework. Our model assumes that the covariance matrix of the innovation vector CT depends on a vector of covariates XT, To ensure the V of XD is positive definite, we use a Cholesky type decomposition to decompose the inverse of the covariance matrix and then parameterize it. We model the phi ij in the lower triangular matrix and the log diagonal elements in the diagonal matrix as linear functions of xt. We refer to our model as the STREX model. Its properties include, by using a Cholesky type decomposition for the covariance matrix and then parameterize it, we can ensure it satisfies the positive definite condition. And the covariates can be either continuous or categorical variables. Furthermore, by assuming the first element of the covariate batch is 1, our proposed STREX model can include the conventional STREX model as a special case. Now, we consider the data Z observed at each of the n locations and at each time t, which consists of the spatial processes of interest with white noise. We assume that the white noise at all locations and times follows a IID zero mean Gaussian distribution with a common variance. Thus, the vector of the data at all n locations at each time t can be represented in this form, where the capital B is a matrix of n spatial basis functions. In addition, we assume all autoregressive matrices are equal, and the mean function has been estimated. The parameter in the STREX model include the autoregressive matrix, the parameter vector in the covariance matrix of the innovation vector, beta gamma, and the variance of the white noise. Now, if capital T observations, we can express the log likelihood in terms of the conditional mean and the conditional variance, both of which are functions of the parameters. So it's computationally challenging to estimate the parameters by directly maximizing the likelihood function. To address this issue, we introduced the ECM algorithm to compute the maximum likelihood estimators. The details of the algorithm is available in our published paper. In this research, we use the multi-resolution spline basis functions proposed by Zheng and Huang. Here we plot the first 50 basis functions at regular points in one dimension. A unique feature of these basis functions is that they are ordered by smoothness. The earlier functions are more smooth, so we can use them to capture large-scale features, while the later functions capture small-scale details. So the number of basic functions decide whether the process is relatively smooth or more complex. To select the optimal number of basic functions, we use the AIC criteria, which consists of two components: the maximum likelihood value of the fitting model and a penalty for the number of parameters used in the fitted model. Then we choose the number of the basis functions corresponding to the minimized value of the AIC function. Next, we represent two applications. First, we apply our proposed model and the conventional STRE model to the log scale our PM 2.5 data in northern Taiwan with 744 time points for 18 stations. We used the first 720 hours of data for fitting and the last 24 hours of data for one step ahead forecasting. For the proposed model, we define the covariance vector based on wind speed intensity. We graph the empirical covariance matrix, the upper two graphs, according to two different wind speed intensity. The left graph represents a light wind condition, while the right graph corresponds to stronger wind speed condition. Similarly, we plot the estimated covariance matrices, the lower two graphs, based on the STREX model for both light and stronger wind conditions. As we can see, the estimated covariance matrix closely align with the empirical ones. This clearly demonstrates that our proposed model is effective in capturing how the covariance structure changes in response to variations in wind stress. Now, let's see some estimation and prediction performance results. In this application, based on the AIC value, the proposed model is preferred over the STRE model. In terms of the MSPE, PC, and the average length of prediction interval, and the CRPS, there is no significant difference in both models. In the second application, we apply the proposed model and the STRE model to the square root scale daily ozone data. In North Taiwan with 276 time points from 16 stations. We use the first 2,066 days of data for fitting and the last 10 days of data for forecasting. In this case, we incorporate wind speed and the sunlight duration information as covariates in the covariance function for the STREX model. Again, we graph the empirical covariance matrix, the left 9 graphs, based on 3 different wind speed intensities and the 3 sunlight duration intensities. For example, the first G11 figure illustrates the empirical covariance matrix for light wind condition with minimal sunlight duration. And the figure G13 shows for light wind condition with long sunlight duration. Similarly, we graph the estimated covariance matrix based on our proposed STREX model for 9 conditions. As we can see, the estimated covariance matrices again closely align with the empirical ones. This illustrates that our proposed model is effective in reflecting variations in covariance structure associated with different wind and sunlight intensities. Now, let's look at the estimation and the prediction performance results for this application. Again, based on the AIC value, the proposed model is preferred over the STRE model. Moreover, our model outperforms the conventional STRE model in prediction accuracy. Now we give a conclusion of this talk. We propose a covariate-dependent spatial-temporal random effects model by a Cholesky type decomposition strategy to make the covariance matrices of the random effects varying with covariates. As shown in the PN 2.5 study, the proposed model effectively captures changes in covariance structure with wind speed intensity. In the analysis of ozone data, we use wind speed and sunlight duration to construct the covariance function of the proposed STRE model. The results reveal a complex relationship between covariance and meteorological variables, leading to improved predictive performance over the STRE model. There are some advantages of our model compared to the existing literature on covariate-dependent non-stationary covariance modeling. Our model is highly flexible to allow spatial covariance structure to change with covariance, which can be continuous or categorical variables, and there is no constraint on the model parameters. The ECM algorithm we used for maximum likelihood estimate of our model is highly effective. It's because there are closed form expressions for almost all CM steps. Some extensions of our proposed methodology are discussed below. First, if small-scale spatial variability is essential, we could add a stationary process to form a full-scale model. Secondly, since the total number of parameters in our model will be large, if the number of covariates is large relative to t, it would be advantageous to apply regularization to reduce the estimation variability. For example, we can use penalized ML with an L1 penalty like the lasso method. And then we minimize the penalized ML to obtain regularized estimate, which can be computed by the ECM algorithm. Okay, my talk is finished. So thank you very much for listening this talk.
Okay, I think the time is right on time. So let's move to the third talk. Okay, thank you. So let's welcome Professor Guo.
Can you see me?
Yeah.
Okay, so I can stop now?
Yes, please.
Okay. Thank you for Nanong's invitation and organization of this section. This is the first time I joined this International Day of Women in Statistics and Data Science. It's an honor. And today I'm going to talk about forecasting and the change point test for nonlinear heteroscedastic time series based on support vector regression. It's a joint work with my student and a co-author, Professor Lee. And this is the outline of my talk that will include 4 parts. The first one, I will give a brief introduction, and then for the problems and the objectives. And the second, I will introduce the estimation method we propose in this study. The third part will be the improvement for the residual-based Q-sum test. And finally, is the numerical analysis and the empirical studies. And the nonlinearity and the conditional heteroscedastic are 2 major characteristics of financial time series data. The SVM-ARMA-GARCH models proposed by Chen et al. Provide flexible model fitting and a good predictive ability for data with these 2 characteristics. Here, the SVR represent for the support vector regression. However, major events such as the financial tsunami and the COVID-19 pandemic often brings shocks and changes to the financial market, making original models no longer suitable for future decisions. Therefore, it is important to detect the occurrence of change points in time to update the model. The objective of this paper is twofold. The first is to improve the forecasting capability for more accurate parameter and the residual estimation for the SVM-ARMA-GARCH time series model. The second is to enhance the detection power of the residual-based Q-sum test of Li et al. When changes occur near the current observing time. So for the first objective, we propose an alternative recursive estimation method, which estimates jointly the parameters of the conditional mean and the conditional variance equation of the SVM-ARMA-GARCH model. So the well-known ARMA-GARCH model has the following form. The return is a linear function of the past returns and the innovation AT, and where the AT square satisfy these linear equations, where the sigma t square represent for the conditional variance of the observation, and AT can be written as a product of sigma t and the epsilon t. Epsilon t has a mean 0 and the variance equal to 1. And for the SVM-ARMA-GARCH model, we replace the linear part of the conditional mean of the return by a nonlinear function by using the Gaussian kernel function, and replace the conditional volatility equation for the AT square also using the Gaussian kernel function. The previous work by Chen et al., they estimate the SVM-ARMA-GARCH model coefficients by optimizing the following 2 risks separately. That is, they estimate the WH, which is the coefficients of the conditional mean equation, and by using the first risk function here, okay? And they obtain the coefficient for the conditional variance by minimizing the second equation here. So what we do is that we modify the first equation by replacing this residual here by some kind of a standardized version. So we alternative using the equation 2 and 3 to obtain the estimation, the parameter estimation of the SVM-ARMA-GARCH models. So that's for the first part. For the second part, the Q-sum test. The second part, the objective is to improve the residual-based Q-sum test proposed by Li et al. Their tests only use time series observation and the model-based residuals, so that it has merits to be simpler and more flexible than other type of Q-sum tests. They consider a location scale models. The time series is a function. The HT here represent for the conditional mean of the time series. The GT here represent for the conditional variance of the time series. The SVM-ARMA-GARCH model we just considered can also be viewed as a location scale model, with HT is this form and the GT is of this form. The goal is to test the null hypothesis, the GT function, and the HT, the conditional mean and the conditional volatility function remain unchanged for the whole period of time. The alternative hypothesis is the H0 is not true. Residual-based Q-sum test of DLO, they consider the test statistic denoted by T sub max, which is the maxima of this statistic TS here. The TS measure the difference between the product of these two, where the A hat is the estimated residual at time t, and tau n hat is the defined as the square of the product of these two terms. Since the statistic TS only involves observations yi and the residuals ai hat, as far as the residuals of the model are estimable, the residual-based Q-sum test can be constructed for detecting change points. So under the null hypothesis, the statistic TS converges weakly to the absolute value of a standard Brownian bridge, BS. Given the significance level alpha, we can find K such that the suprema of the absolute value of a Brownian bridge greater than K equal to alpha. So we will reject H0 if the Tmax is larger than this K here, which is then becomes the critical value. Instead of using Tmax, we can also consider using the Tmax scale, which scale the TS statistic at the maximum point, okay? Because this is the standard deviation of the variance of the TS. Further, obtain the limiting distribution of this Tmax scale and use it to improve the power of the Kolmogorov-Smirnov test. Although the Tmax scale can overcome a shortcoming of Tmax, it only considers the standardized Tmax, but not the standardized value at other time points. As such, we here construct a time-varying control limits for TS based on the fact that we use the standardized version of the Brownian bridge. The limiting distribution of the standardized Brownian bridge, and we can obtain the quantile of this statistic. But for small s, there can still be some concern regarding excessive type 1 errors in the implementation. For example, if we consider an AR1 model, the rejection rate of the null hypothesis out of 500 replication is 0.114, which is much larger than the significance level alpha equal to 0.05. So we propose an adjusted control limits for TS defined as the following. That is, we consider a control limits, upper control limits, which when S less than or equal to S star is a constant K. And for S greater than S star, which is the intersection of the blue curve and the red line here. So we use simulation to obtain K star by controlling the type 1 error. So this is the proposed adjusted control limits for TS. So do I still have time? I noticed that the time is 6:50 now. So can I continue or I should stop here?
I think you still have some time.
Still have some time? Okay.
5
Then
minutes.
I will quickly, maybe I can just share the real example, okay? We use the test on the Baltic Dry Index, BDI. This is the index issued daily by the Baltic Exchange in London. The BDI is a composite of the cap size, Panamax, and the Supramax temperature averages. This is reported worldwide as a proxy for dry bulk shipping stocks and the general shipping market bellwether. We use the BDI daily log return data to perform a one-step ahead forecast. We split the data into the training set from 2015, January 1st to 2016, December 31st, and the test set from 2019, January 1st to 2021, April 6th, concurrent with the validation set from 2017 to 2018. We construct the SVM-ARMA-22 and the GARCH 11 model, and the orders of the ARMA and GARCH are determined by the ESCF and the AIC. We apply the grid search to the validation set to determine the free parameters of the SVR part. We also consider 3 neural network models for comparison, including the RNN, LSTM, and the GRU models. The forecast performance of the 6 models for the BDI, the proposed SVM-ARMA-GARCH model has the smallest, using the proposed estimation method ARE, attains the smallest normalized mean square error and the smallest sign error. This table shows that the neural network model has better predicted ability than the traditional time series model, ARMA and the ARMA-GARCH, but underperformed the SVM-ARMA-GARCH model. And further, the ARE method performs better in the SVM, ARMA, and the GARCH models. And to perform the residual-based Q-sum test, we use the residuals. We use the residuals to obtain, based on the ARE method, and apply the 3 test statistics to the BDI data to detect a change point from 2019 to 2021. In this test, we use the rolling window scheme with the width of 1 year and the 1-day movement. When the change point is detected, the point exceeding the control limits the most is declared as a change point. One can guess that the true change point occurred on 2019, December 24th, as the COVID-19 outbreak began at the time, and triggered a sudden change in the global financial market, resulting in of crash in stock prices. To examine this, the 3 tests are conducted. The results shows that TSUCL detect a change point most quickly on 2020, January 10th, while both Tmax and the Tmax scale detect a change point on 2020, June 11th, which is quite late compared to the first test. And the second change point is claimed to be on 2020, March 30th, as the price of Brent crude oil fell 9% at the date to US from $23 per barrel, which was the lowest price since 2002. As all ships in BDI needs oil to travel, the abnormality of Brent oil led to trigger on a series BDI change. In this case, the proposed TSUCL detects the change point, the first on April 14, and the second is the T scale max, and the third one is T max, respectively.
Excuse me, Professor Guo, please, and
Yes.
1 minute,
So should I stop now?
please, to the end.
So this finding reveals that TSUCL can detect change about a half month after the occurrence of such big events, a lot faster than Tmax and the Tmax scale, which strongly affirmed that the validity of our proposed method when used in tandem with the Loing window scheme. Okay, so here's the conclusions. So I will just say that all the results affirm the validity of the proposed method. Okay, so that's the references, and thank you for your attention.
Thank you. I think this session will end here, and thank you all speakers and audience for your participation. We will leave the floor to the next session. Thank you.
Thank you.